Symphony. Okay, the first thing I actually want to do, this is actually good enough. Did we ever figure out a way to mute this or no? Just turn it off, right? What is it?
Blue one. Blue
Button.
one.
Last time they got all shaky and hit me a little bit. No one hated me. I turn it off, or is that not the best way to do it?
I don't know. Find out again.
Okay. I just want to see what's on the board a little easier. So we're just turning it off. Okay, that's fine. Not a problem. Thank you. So this is kind of a state of the class, kind of where we are and what we've done so far. And I tried to organize it as best as possible from the top down. So mostly what we've been talking about is this idea of machine learning. Obviously the course is called data science and we do more things than just machine learning. But machine learning is kind of where we spend most of our time, most of our discussions. So I kind of tried to separate out what we've done so far. So we kind of start up here with machine learning as a general idea. And there are two types of machine learning. On the left, we have supervised, and on the right, we have unsupervised learning. We break down supervised even further to say there's two types of supervised learning, regression and classification. The regression is trying to predict a continuous response. Classification is trying to predict a categorical response. And you can see that we've only actually technically learned one type of regression called linear regression. And we've actually learned two so far, classification models, logistic and KNN. Those are both classification modules. The one that I've starred is what we're going to be learning today, so I'm putting it up there as we're going to learn naive Bayes today. Over here on the right, we have unsupervised, which is a little bit more bare because it's kind of a problem that less people work with, but still is important to know. There's two types of unsupervised learning. There's clustering analysis, which we've actually done already with the team means clustering. And there's this thing called dimension reduction, which we have not done yet. So this is actually the last form of machine learning, which we haven't actually talked about in this class yet. We're going to talk about it because we haven't done it yet. I've also included metrics for each one, because sometimes I still get questions like, hey, why is my accuracy not working for my regression model? Because accuracy doesn't work for regression models. So I kind of put them on the board as well. So for regression, I've listed some of the metrics that we've talked about, the root mean squared error, R squared, the mean absolute error. There are other ones that we've touched upon, like p-values isn't really a metric, but p-values is another way of quantifying relationships. But these are kind of the three main regression metrics that we've talked about, root mean squared error, R squared, and mean absolute error. Over here in classification, I put accuracy, sensitivity, specificity, and the one that's starred that we're going to learn today is called ROC, the receiver operating characteristic. So we have not learned that yet, but that is a metric for classification. And over here in clustering, we have three metrics, the silhouette coefficient, cohesion, and separation. So I hope this kind of helps, and I'm not going to erase this for a while, so if you want to take pictures later or come up here and whatever, I'll let you do that. But I kind of hope this served as a, first of all, when you walked in here, you started here. So in the last 11 days of this class, we've done all of this. So kind of think about that. We're only halfway through the course, and this is already what we've done. We've learned 4 separate machine learning, well today, including with 5 different machine learning techniques, bunch of statistics, bunch of metrics, bunch of math. I'm super proud of you guys. We're going to keep trucking along. So, the purpose of today's course is to go even deeper into classification. Why go even deeper into classification? Why not touch more on regression? Why not touch more on this dimension reduction thing that we've talked about? Well, we've come to a point where we all have seen, at least, me or other people or between blogs and articles, we've been experiencing different types of modeling techniques, and we're now able to look at a brand new concept and try to apply old techniques to it. So when I say naive Bayes is a classification technique, the first thing that should come to your mind is, well, we're going to see the confusion matrix, we're going to see accuracy, we're going to see sensitivity, and we're going to see specificity. And you'd be absolutely correct. Because when I talk about a classification model, all of those things I just said will always be relevant, which is why the terminology is so important. Like if someone comes up to you and says, I have this cool classification model, the first thing you should say is, cool, let's see a confusion matrix. Let's analyze this. Let's go deeper into this. That's why the terminology is so important. And that's why sometimes in the conversation we say, oh, I have this awesome classification model and my root mean squared error is through the roof. You can say, bullshit. Well, in a nicer way, depending on who you're talking to. Say, BS. You can't have a root mean squared error because you're doing classification. You're wrong. I'm better than you. So, ha. So you can have these conversations now. Not saying you should, but you can have them. And you can rant to people on the internet about machine learning, which is so much fun. Not that I do it. So again, I will leave this on the board. I'm not going to erase it for the entirety of the class, but I do need the board. Again, I'm sorry. It was kind of the only place big enough. I think this should work, what I just did. I think it worked. It's turning on. The light is shining in my face, which is a good thing. Me. No. Okay. Okay. 2 means correct. Awesome. That was way smoother than usual. All right. So the first thing that we are going to talk about is this ROC. It's a new metric for classification, which we're going to be going into with our naive-Bayes classification. Why learn it now? Well, if I had come at you with 5 different classification metrics on the first day of classification, that would have been a little bit much. Also, ROC is a extension upon accuracy, sensitivity, and specificity. So it requires knowledge of those 3 things to even understand what the ROC means. So we're going to go through all those 3 things again and then talk about the ROC. So here is nothing new. Confusion matrix. We have our actual yeses on the bottom, actual no's, predicted yeses. It's a table to describe the performance of a classifier. So an example is that we always use a test for the presence of a disease. No means a negative test, yes is a positive test. So if I ask you, for example, how many patients were there in this entire experiment, what would you say? How many patients in total were there? Total patients that walked into this office. 165. It's a summation of all of them, right? So this is a breakdown of all 4 possible things that could have happened to them. But if you add them all up, that's how many different people walked into the office that one day. How many times was the disease predicted?
165.
Well, not quite.
Oh, sorry, predicted.
Predicted. So how many times did the test say, yes, this person has a disease? Say it again? 10? A little bit more. 110. So this column here is a predicted yes. So this column is everyone who the test said yes to. Now, of those people, how many of them actually had the disease? 100, exactly. Of the people, so this column, who had the disease, how many of them did actually had it? 100. Now, of the 165 total, how many people does not have the disease? Say it again?
10.
Not quite. 60. So put your answers together. 60. This row is people who actually don't have it. So when I say of the 165, how many people just don't have it flat, no matter what the test said, don't have the disease? That's the first row. 50 plus 10 is 60. All right, one more. One more. Of how many people did the test say you don't have the disease, but they actually did? 5. Perfect. Test said no, actually had it, 5. So from the confusion matrix, we can look at some basic terminology. True positives, which is a number. True positive is not a ratio, is not a fraction, it's an integer. True positive is the literal number of people who was a true positive. The test said yes and they had it. It's not a ratio. True negatives, again, is an integer. It's the physical number of people who the test said no and the test was right. They didn't have it. That's 50. False positives is when the test said yes, but they didn't have it. That's 10. False negative is when the test said no, but they did have it. And that's 5, bottom left. So from this, we can define accuracy. Overall, how often was the model right? And that's our true positives plus true negatives divided by the total was 91%. So of the times it predicted, it was right 91% of the time. We have a misclassification error, or misclassification rate, or an error rate, which is just 1 minus the accuracy. Overall, how often was it wrong? Which is false positive plus false negative over all of them, which in this case is 0.09, 9%. So it's right 91% of the time, wrong 9% of the time. So that makes sense that they add up to 100% because the test is either right or wrong. We can go even more in depth. False positive rate, when the actual value was negative, how often was the prediction wrong? So when the actual value was negative, that's the first row, out of 60 people, how often was the prediction wrong? That's 10 out of 60, which is 17%. Sensitivity, when the actual value is positive, how often was the prediction correct? So now we're only looking at the times when people had the disease. So actual guesses is the second row. So of those 105 people, how often was it right? 95% of the time, also called sometimes a recall rate or true positive rate. Sensitivity, all the same things, different words. Specificity is when the actual value is negative. So first row, out of 60 people, how many times was the prediction correct? 50 out of 60, 83%. So we've seen this before. We know the difference between accuracy, sensitivity, and specificity. It means different things in different times and places in terms of prediction. In terms of prediction, which do we say is usually better? Or rather, which carries more weight in terms of a disease prediction? Sensitivity or specificity? If I told you I have one test with a very high sensitivity, low specificity, versus a test with very high specificity and low sensitivity, which would you rather take? Well, if the test had a high sensitivity, describe to me what that means. If the test has a high sensitivity, what does that mean? Yes, that's right.
It's correct more often, or it has a high rate of being correct?
Assuming what? That's the difference. In sensitivity, it has a high correctness rate, assuming I have the disease. Because this is when the value is positive. So assuming I have the disease, if I knew I had the disease, well, if I knew how it would be here in the first place, but assuming I have the disease, I'd rather have a sensitive test because it's better at picking that up. If I don't have the disease, the specific test is better at picking that up. So which one is better? This is arguable. This is debatable. This is not a yes or no clear-cut answer.
Maybe it depends on what it is and the severity of it, what the predictions are. For example, if you have cancer and you need to go through chemotherapy versus, I don't know, you have, I'm trying to think of something more mild. Maybe you have some cold.
Fair enough. Lyme disease is actually, well, obviously don't let it untreated for too long, but for a while, it's not that bad, from what I understand. I've never had Lyme disease. So it means different things in different problem domains. So an ROC AUC is a kind of combination of the two. So every email that we're going to look at today, every email address is going to be assigned a spamminess score by our classification algorithm. It's going to say 99% spam or 2% spam, which makes it ham, which is a good email. So it's going to be, if you think of it as a predict problem. Assume we do a predict proba on each email, and we get a probability that it's in class 1 or 0. To make our predictions, we have to choose a numeric cutoff to classify as spam. So, generally, we call it a 0.5% split. If it's above 0.5, call it spam. So if it's 99% positive for spam, call it spam. If it's 2% positive for spam, don't call it spam, call it ham, which is good email. So generally we say 48%, okay, that's, we could say 48% would be a good cutoff for spam. So it depends on what cutoff we choose. Usually it's 50%, but we can change that. we could say only classify it if you're 90% sure. If you're 90% sure it's spam, call it spam. Otherwise, just let it go. It's fine. And that, if you change our threshold for predictions, it actually changes our sensitivity and specificity, which we're going to see in the code. The ROC, AUC, is actually a way to visualize how well our classifier is doing without choosing a cutoff. Without actually saying 50% or 51%, 49% or 52, 48. Without having to choose a dead set cutoff, we can visualize how well it's doing. And the way it does it is, it plots our true positive rate on the y-axis and our false positive rate on the x-axis. So in this case, true positive rate, when the actual value is spam, because true we're defining as spam. So in the previous true it means had the disease, here is true means is spam. True positive rate, when the email was spam, how often was our prediction correct? False positive rate is when the actual value is ham, as in it was a fine email, how often was the prediction wrong? So we actually plot them against each other. Why? Well, if we choose different cutoff rates, so here on this, in the filled in part, I'm choosing arbitrary cutoff rates. What that means is, 50% means if it's above 50%, call it spam. If it's below 50%, call it ham. And 85% cutoff means if you're 85% sure it's spam, call it spam. If you're 84% sure it's spam, don't call it spam. Call it ham. That's not sure enough. So this is us defining how sure you want it to be. If your cutoff was 50%, let's say you had a true positive rate of 75% and a false positive rate of 25%. Now, put it this way. If your cutoff were 0, what is 0? What does that mean? If your cutoff is 0, what does that mean? Everything is spam. If your cutoff is 0, you're literally saying everything is spam. Your true positive rate, when the actual value was spam, how often were you correct? Always, because you're always saying spam. It's 100% true positive rate, which automatically sounds great, right? You have a true positive rate of 100%. But here's the problem. Your false positive rate, when the actual value was ham, how often were you wrong? Every single time. Every single time there was a ham email, you got it wrong because you just said, you kept saying spam. So this is terrible. Likewise, when your cutoff is 100%. If your cutoff is 100%, what does that mean? Everything is ham. Let everything through. Your spam filter actually does nothing. So when it was spam, how often were you correct? Never. When it was ham, how often were you wrong? Never. Theoretically, you want to maximize your true positive rate and minimize your false positive rate. That's your goal here. You want to be true positive rate as good as possible, false positive rate as low as possible. So for example, if I have a cutoff rate of 65%, my true positive rate is 50, and this is using this data, exactly. This is not well, it's theoretical in nature, but all of this is coming from this sample over here on the left-hand side with these 8 emails. So if we chose a cutoff rate of 65%, let's actually look. Which of these are over 65%? 1, 2, 10. Right? Yeah. Only 2 of them are over 65%. And they're both happen to be spam. So, if only these 2 are being classified as spam, everything else is saying ham. Only the top 2 are saying spam, the filter says everything else is ham. When the actual value is spam, how often was I right? There are 4 spam emails. How often was I right? 50%, the top 2. But these 2, because the cutoff is 65, I didn't classify them. When the value is ham, how often was I wrong? Remember, I said ham for all of these. So, how often was I wrong when I said when it was actually him, how often was I wrong?
Twice.
Never. Because remember, all of these, the spam filter said fine. So for all the actually fine emails, it was right. It only actually predicted spam twice in the top two. If the cutoff is 65%, only these two values are above 65%, only these two emails were classified as spam. Everything else, it said go on through. Of those 6 emails, it said go on through. 4 of them were actually fine. 2 of them were not. It let through 2 spam messages that weren't supposed to be let through. So as we change our cutoff rate, our true positive rate and our false positive rate, our sensitivity, our specificity, all the accuracy, all of those metrics change as soon as we change the cutoff. The ROC, AUC, is a visualization of not having to choose it. And this is what it looks like. If you plot those points, if you literally plot 1, 1, 0.751, 0.51, 0.251, you actually plot those points on a graph, it looks like this. And we'll see a visualization in Python as well. But this is what happens when you actually plot those points. What you want your curve to kind of shoot up, hug this upper left-hand curve, and then smooth off like this. So, right, so you have false positive rate on the x-axis, true positive rate on the y-axis. You want a low false positive rate and a high true positive rate. So this is actually looking like kind of a good model, all in all, because the true positive rate shoots up, and the false positive rate kind of stays towards the left-hand side, which is the lower side of things. So question, theoretical question. Would the ROC curve, which is what this is called, the ROC curve, and the AUC, AUC stands for area under the curve. AUC is a number between 0 and 1. And if you remember calculus at all, it doesn't really matter. But it's the literal area underneath this curve. And because this is a 1 by 1 square, the possible range of values are 0 to 1. So would those numbers change? Would the ROC change if the scores changed, but the ordering remained the same? So if we changed the scores, but we didn't order anything at all? And the answer is no, because the ROC curve is only sensitive to rank ordering. Essentially what that means is, so in this specific one, we changed all of the scores that we gave the emails. So if you remember from here, so in this one, so let's look at the second email with the 0.82. Now it's 0.98. So nothing is changing except for those scores right here. And it actually would not change the ROC if you changed those scores. Because the ROC is a visualization of every single possible threshold cutoff. The ROC is a fantastic metric to judge the overall quality of your classification model. Without having to say, well, assuming the 50-50 cutoff, or maybe by changing to 75-25, it'll be a little bit better. It's a way of showing you how well your model is doing overall, without having to be too specific and, okay, what's my cutoff point? Which is why if we change the scores, it doesn't matter. Because the cutoff point is irrelevant, because it tries all possible cutoff points. Let's actually look at some example in Python. So the first code I'm looking at is called confusion ROC. It's not because you're all confused, it's because of the confusion matrix. 12 underscore confusion ROC. I've already written the data. And here's what the data is. It's two new sets of data today. The first new set of data is this one. It's actually loan defaults. So every single row represents a different loan taken out. And what we're trying to predict is defaulting. Is someone going to default on their loan? We have a couple of predictors. We have, so the first one is actually our response, default, 0 or 1. 1 if they did default, 0 if they did not default. So 1 is, I guess, bad in this case. 1 is they defaulted, 0 is they did not default. The second column is one of our predictors. It's student, whether or not the person was a student, no or yes. And yes, I actually put it as a string, just to mess with you. No. Balance, does anyone know what balance means? What is balance? Yep.
The amount of your loan.
Yep. Balance is how much they have left. And income is their income, is how much money they make, as reported by them and so on and so forth. So we have 3 different predictors, 1 response. Is this a classification or a regression? And why? Who thinks it's a regression? Who thinks it's a classification? Who doesn't know? What does classification mean?
I raised my hand the last one.
I know, it's like a lot. What does classification mean?
Multiple options you gotta choose.
There are multiple options from our response, right? The thing we're trying to predict. What is it about those responses that makes it classification and not regression now? Or categories. It's not a number scale. You know, we're not trying to predict a number scale. We're trying to predict one of 2 things. Yes, they defaulted. No, they did not default. When there's only 2 or 3 or 4 options, that's called classification. You only have a limited number of options. If it were regression, the thing we're trying to predict has infinite number of options. If you're trying to predict a dollar amount, you have an infinite number of decimal points that you're allowed to use. So in a regression problem, we're trying to predict a continuous number. In a classification problem, we're trying to predict a category. One of 3 things, or one of 7 things. You could theoretically have 10,000 things, but as long as there's only 10,000 of them, it's still classification. So this is a classification because we are trying to predict true or false, default or not default. That's why it's classification. So I'm only going to use one predictor, balance. How much I have left. Y is the thing I'm trying to predict, my response, X and Y. I will use my train test split to split this up into a training set and a testing set. So I've set my random state as well so that we all get the same number when we do this. So I've set it into X train, X test, Y train, Y test. Does someone want to remind me what exactly I just did in that line of code? So if X is all of my predictors, my balance, Y is all of my defaults, 0s and 1s. What is X train and Y train? What is X test and Y test? X train is a random 70% of your data. That's it. X train is a random 70% of your predictors. Y train is a random 70% of your response. X test is the remaining 30% of your predictors. Y test is the remaining 30% of your response. And random state equals 1 just means that we're all going to get the same random numbers. So let's actually do a logistic regression, which is still a classification. Remember, ROC is for classification. We could use any classification model we want. So I'm just going to use logistic regression as my classification model to demonstrate. I will import it. I will instantiate it. I will fit it. Always fit it to the training data. Fit it to the training data. Score it on the testing data. So fit to X train, Y train. Score it on X test, Y test. Score will automatically tell you your accuracy. So this model just had a 97% accuracy on this one split. So it was correct 97.4% of the time. 97.5 if you round. Automatically, that sounds great. Here, I am doing same thing, using actual scikit-learn metrics to do accuracy instead. No difference in numbers or anything. It's just a different way to do it. If whatever you find easier to do. Now, here's the question. A 97.5 accuracy rate, is that good? I hear, yeah, why not? 97.5 is a really good number. Here's the question. I wonder how many people actually defaulted. Like, for example, let me put it this way. This model is right 97, let's say, 97% of the time. Fine. What if 99% of people never defaulted? If 99% of people do not default, what's better? This model or some intern standing in a room saying, oh, they're not going to default? Because that intern will be right. A stopwatch is right twice a day. That intern will be right 99% of the time because 99% of people don't default. So 97.5, don't be fooled, is a great number, but let's look at something. The null accuracy rate. If we take the mean of our test, our mean is 0.03. What does that mean? Well, our test is a bunch of zeros and ones. 0 representing they don't default. 1 representing they do default. So how often does someone not default? 96.8% of the time. So just under 97% of the time, they don't default. Like if you just said, so put it this way, if that intern is standing in a room saying they're not going to default, they're not going to default, they're not going to default, that intern is right 96.8% of the time. Our model is better than the intern. Congratulations. Your model is better than some person just blabbering off the same answer over and over and over again. Which is exactly the point I was trying to make here. If your cutoff is 0%, that's the same thing as saying spam, 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 default, 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 default. If your cutoff is 1, that's the same thing as saying email's fine, ham, 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 ham. Not gonna default, not gonna default, not gonna default. Always saying not gonna default. If someone has a cutoff of 1, they'll always say not gonna default, not gonna default, not gonna default, and they're gonna be right 96.8% of the time, period. Which is already, by our definition, by our standards, quote unquote, really good. But the point of machine learning is to be better than that. The point of machine learning is to be better than the null accuracy rate. The person just saying the same answer over and over and over again. So, which it is. In this case, 97.5, which was the model score, is better than the person just saying the same answer over and over again. It's like in the stock data. If most of you, if not all of you, most of you at one point set it to a classification, right? True if it went up, false otherwise. Well, if you did that, the stock price went up about 60-odd% of the time. So if you just kept saying up, 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 you would be right 60% of the time. If you could beat 60% of the time, so it all depends on what your null accuracy rate is. It all depends on the difference between saying the same answer over and over again or using our machine learning model. And that's what the ROC AUC is trying to tell you. How much better are you than the null accuracy rate. So we have our confusion matrix for this particular case. We also have NLTK has a confusion matrix. It's a little bit nicer. I mean, barely. It's a little bit nicer in the sense that it kind of shows you the row as your reference and your column as your test. So it's kind of showing you what the columns and rows mean. But that being said, nothing is still changed. So our sensitivity is still the percentage of correct predictions when the reference was true. So 21 divided by the second row is 26% of the time. Ooh. Our sensitivity is 27%. Our specificity is 99%. What does that mean? Someone explain to me, in terms of loan defaulting, what does it mean? Start with that our specificity is 99.8%. That's a really close to 1. That's really good. So what does it mean that our specificity is 99.8%? When what? Assuming what? Say again?
Model says yes, it's right.
Kind of flipped. So the assumption for sensitivity, this is tricky. The assumption for sensitivity and specificity. For specificity, when the reference value, i.e. when the person did not default, the model can pick that up 99.8% of the time. When the person is not going to default, the model is right 99.8% of the time. So it's really good when the person is not going to default. It's good at picking that up. Flip that. Sensitivity. And remember, you have to remember what true and false mean. True means default. True means default. That's a bad thing, I guess, for the bank. But true means default. So sensitivity, when the person's going to default, the model picks that up 27% of the time. Yeah, not so great. So the model is a lot better at picking out people who are not going to default than it is at picking out people who are going to default. Is that useful to the bank? Not quite, because they really want sensitivity to be better. They really want a higher sensitivity. They want a higher sensitivity because they don't care if the person's not going to default. That's what they expected. They want to be able to catch the people who are going to default and stop giving them money. So a higher sensitivity to the bank means better at figuring out who's going to default on their loan. We can show this as a histogram. Here's a histogram of predictions that someone is going to default. Notice how right skewed it is. Most of the predictions are less than 0.1% that someone's going to default. Now, here's where we're going to play with the cutoff rate. Using NumPy, probs is a list of probabilities that somebody is going to default. So this first guy, 0.005, so 0.5% that they are going to default. If we set the cutoff rate to 0.5, we get exactly what we had before, the same numbers in our confusion matrix. Is everyone able to plot the confusion matrix and getting the same numbers as me? I have to stop and make sure. Yes? Cool. I'm going to change the cutoff using NumPy. I'm going to say, okay, well, because my sensitivity was bad, and this is kind of where terminology makes sense. If it's not sensitive enough, I'm going to tune back the threshold. I'm going to say, okay, you know what? If you say 20% default, say you're going to default. That's what I'm saying in this line of code that I'm highlighting. When the probability of defaulting is greater than 20%, just tell me they're going to default. Otherwise, say they're fine. When I do that, here's my new confusion matrix. Notice a few things. The number in the bottom right, which is my true positives, the type of the people who were predicted correctly as defaulting, more than doubled. I'm now catching more than double the amount of people who are defaulting when I tune down my threshold. My accuracy has decreased to 95%. It is now actually worse than the intern saying default, 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 default. But here's where the intern doesn't know anything. All they can do is say, or sorry, not default. All the intern can do is say not default, which is totally not helpful to the bank because they need to know the people who are going to default. That's what matters. So here's our new sensitivity. Our new sensitivity, if you recall from our previous one, which was 26%, this is a lot better. Again, more than double. When someone is going to default, our model will catch it more than half the time. Of the people who defaulted, we caught over half of them, which is better than 26%. That being said, our specificity took a hit. Our specificity, which was once near 100%, 99.8, has now dropped dramatically to 96.6. But again, what does specificity mean? Remember, specificity is if it's false, it was correct. False means not defaulting. What does that mean if our specificity went down? What is our model doing more? Yeah, that's right.
It's identifying people who would otherwise not default as likely to default.
Yes, it has done the following more often. People who are fine or are not going to default, the model is saying they're going to default more. Because when I decrease the threshold, more people are slipping through the cracks and saying, oh, yeah, this person's going to default. Flag them down, but really they're a model citizen, they're not going to default, they're fine. Is that so bad to the bank? No. Why? What does that mean? If specificity went down, which means they're flagging more people as going to default when they're not going to, what does that mean for the bank? Say it again? Yeah, it's just more time. That's all it is. All that's going to happen is someone's going to be on the phone with someone and asking, hey, are you okay? Are you going to default? And they're like, no, I'm pretty good. Thanks for checking up, though. That's all that's going to happen. This person is now not suddenly going to default now that the bank is checking up on them. They don't care. They just want more people to be classified as defaulting when they're actually going to. They don't care that now this one teller has spent 2 hours of their day calling people who aren't going to default, thinking that they're going to. That doesn't change anything. What does change is that where they used to only catch 21 people who are going to default, now they're catching 45 people who are going to default. So we have to keep in mind the relativity. We were once only catching 21 people, now we're catching more than double the amount of people who are going to default. And the only bad side is, some of my employees are spending time talking to people who aren't going to default. That's it. That's the bad part. So it's not like cancer, where if you say you're going to default and you're not, you go through chemotherapy. No, in this case, if you say they're going to default, you're going to get a phone call. That's what's going to happen. Your dinner will be interrupted once more by your friendly Bank of America. That's what's going to happen. You're not going to go through chemotherapy. So sensitivity and specificity mean dramatically different things in different problem domains. In the bank, specificity can take a hit because they really care about sensitivity. They really want to know the people who are going to default. They don't care if they're misclassifying people who aren't going to default. Because again, all that means is a couple of phone calls to make sure. Here's what our ROC looks like. False positive rate on the x-axis, true positive rate, otherwise known as sensitivity, on the y-axis. As our threshold is changing, every time our threshold changes, that's a new point on the graph. The one downside is you can't look at a point and say, oh, this is with threshold 0.65, or this is with threshold 0.35. You can't say that. Again, every metric has pros and cons. The big pro of the ROC is you're getting an overall idea of how your model is doing without choosing 0.5 or 0.2. It's showing you all possible options, all possible thresholds from 0 to 1. It's starting from always say default and ending at always say don't default, which is why our graph will always start at 0, 0 and always end at 1, 1. Because it starts at not defaulting, not defaulting, not defaulting, not defaulting, and ending at default, 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 default. If your line is above this diagonal, the diagonal from 0, 0 to 1, 1, if your line is above that diagonal, in general, your classification is doing well. It is doing better than the null accuracy rate. The AUC is, again, part of the scikit-learn metrics. So you just do metrics.rocauc, and it says 0.94. Again, it's a number between 0 and 1. The closer to 1, the better. You can use ROC in your cross-file score. So your cross-file score, you can use accuracy, mean squared error. You can also give it instead ROC_AUC. And it will tell you your average ROC for 10 folds is, again, about 94.8. Now, here, I'm going to give it balance and income. Remember, all I gave was balance. I only gave it the balance predictor, and it did a pretty good job. We never even thought to add another one until now. Now I'm going to add their income. Now we're going to try to think about their income and how much they have left. And do the same thing. Cross-file score with ROC-AUC. ROC-AUC is a general predictor of how well your classification is doing. And if you add income, your accuracy, or your ROC, shoots down to 0.59. What does that mean? What does that imply? Patrick, what does that imply?
That you shouldn't do it
Why not?
because your performance gets worse.
Exactly. That's the simplest sentence. That's all I wanted to hear. Why is income not a great predictor? Because my metrics don't reflect that it is. My metrics were higher without income. Does someone work in the finance industry and kind of want to maybe try to explain why income doesn't matter? Can someone name someone, here's a really good one. Can someone name a really wealthy rapper who recently went bankrupt / defaulted in the last week? 50 Cent. 50 Cent, notorious, entrepreneur, rich guy, get rich or die trying. He, almost died trying, he got shot. But he defaulted on all of his loans. He went bankrupt. So it doesn't matter how much money you bring in. That's not a great predictor of if you're going to default on your loans. Because what matters more is how much you owe. I could owe $1 million. I could make $1 million a year, only owe $50,000, but not be able to pay that off. because I'm spending my $1 million everywhere else but my loans. So what this model is implying is that income actually is not a contributing factor to defaulting. It's actually more about their balance, how much is left on the loan. All right, so we have a new metric in hand, ROC, AUC. Cool. Righteous. Radical. Tubular? I'm out of words. So, when you are assessing your classification model, accuracy, sensitivity, specificity are still super important. The problem, you tell me. There's accuracy, sensitivity, and specificity, and then there's ROC, AUC. There is a glaring difference between these three over here and this one over here. Accuracy, sensitivity, and specificity, ROC, AUC. What's the main difference between the two? What does accuracy, sensitivity, and specificity imply? I'll give you a hint. I can change all three of them between these lines of code. You had your hand up?
I was just going to say something about the threshold, right? Changing the probability.
If I change my threshold, all three of those numbers change. ROC won't. ROC is like a rock, which is how I remember why it's great. The ROC sounds like rock. It is your rock in your classification model. That number will never change even if you change your thresholds. It is a general predictor of how well your model is doing without having to set a threshold. Whenever you've been doing your accuracy, sensitivity, and specificity, you have all been assuming a 50% cutoff rate. That above 50%, call it true, 50 or below, call it false. Go back and try some of your same problems by changing the threshold and see if your accuracy goes up or your sensitivity goes down or what happens. But your ROC will never change. Your ROC is a rock in your classification. Won't change no matter what your threshold is. Does that mean your ROC is your tell-all, end-all metric for everything? No, it never does. There is no such thing as a tell-all, end-all metric for a classification or regression model. Sorry. Your ROC, your ROC, AUC is great because it's an overall description without having to set a threshold. The con, there's no threshold. You don't actually know your sensitivity, specificity, and accuracy. You can't quantify how well you're doing. To actually get your accuracy, your sensitivity, those numbers that actually matter in metrics land, and the one that when you publish your paper, your accuracy is looking at published, not your ROC, AUC. To get those, you have to set a threshold. To be able to walk confidently into a patient's office and say, this test is 99% accurate, you have to set a threshold. You can't walk into, if someone says, the doctor's like, oh, my new disease test has an AUC of 0.99. That's great. So do I have it or not? They can't answer that question. They can't actually answer the probability of you having the disease with an ROC. So there are pros and cons, as always. Which leads me to probability. Now, I'm going to go ahead and assume that most people did not have a chance to go over the probability refresher on the GitHub page that I posted on Monday. It's fine. It's fine. We're going to go through some probability today. So we're going to go through probability and Bayes' theorem, which is probably one of, if not the most important probability theorem out there. And then naive Bayes classification is a machine learning model that is entirely dependent on Bayes' theorem. Now, this slide deck is fairly interactive. I'm going to be asking questions about probability, a little tiny bit of math. A little bit of math. Okay. Get used to circles, because everything is about to be a circle. Your life is about to be a circle. The world is flat from now on. Let's pretend you're flipping a coin, which is a circle. This diagram represents the universe of all possible outcomes, otherwise known as events, all possible things that might happen. The universe is known as your sample space. Your sample space is the universe of all things that could possibly happen. What are the mutually exclusive events that make up the sample space for a coin flip? To define mutually exclusive, for those of you who might have forgotten, mutually exclusive events are events that cannot happen at the same time. So when you're flipping a coin, what are the events that cannot happen at the same time? Heads and tails. Cannot happen at the same time. Gold star. Just want to keep it. Yes, next. No. Now pretend that our universe involves a research study on humans. So bigger jump here. A research study on humans. That's us. Event A here is people in the study who have cancer. If our study has 100 people and A, people who have cancer, has 25 people, what is the probability of A? 0.25, 25%. I will pretty much, from now on, describe all probabilities in decimal form. So 0.25 is 25%. What is the max probability of any event? Of any event anywhere in the world? 1. 1. I might do it as a fraction to make the numbers clear, so 100, 100, 25, 25. 0.25. Cool. Gold stars for like half of you. You didn't say anything, so you didn't get a gold star. I like to single you out. I don't know why.
Me?
Yes.
I actually finger up.
You got a finger up?
That was one.
Which finger?
That's one.
Okay. Great. This represents this same set of people, except everyone is given a test. Event B, I'm making this very painfully slowly clear because A and B are about to get wild. B is everyone for whom the test is positive. What portion of this diagram represents a subset of people with a negative test? That's the white space. So when I color in B, the white area between the small circle and the big circle are the portion of the diagram for people with a negative test. Because these people inside have a positive test. So far circles make sense? So far circles make sense. Oh, crap. A and B. Now, A and B are two events of a larger sample space. From the same study, we can show them in the same universe, which is the larger circle. Because A and B happen in the same universe. How would you describe the cancer status and the test status of people in each area of the diagram? So let's start with the white space. What does white space represent? Remember, A are people who have cancer. B are people for whom the test is positive. What is our white space? People who don't have cancer and for whom the test is negative. How would you describe people in this light red part? I apologize if anyone was red-blue colorblind. Can you be red-blue colorblind? No, you can't. It's red-green. Ah. This is lighter red. Sorry, what is it?
People who have cancer
And?
and tested positive.
Ah, this is the tricky part. A, this circle is people who have cancer. But if you're not in the center part, you're not in B, which means your test was negative. What if you're in this blue part? This kind of crescent blue part. What does that mean? But
But you don't.
you don't have cancer. So what is A and B?
And tested positive.
And you have cancer. There's always two events we have to be aware of. you have cancer and the test is positive. So pink, cancer, negative test. Purple, cancer, positive test. Blue on the right, no cancer, positive test. White, no cancer, and a negative test. Here is the confusion matrix. So our A and B, 20, that's our true positives. Our true positives are in that little purple space. Our true negatives are people in the white space. The white space is the biggest one. That's our true negatives. Our 5 on the A, people who have cancer, but the test said no, what is that called? When the test said no, but they actually had it, what is that called? False negative. The way to remember it, false means the test was wrong. Negative is what the test said. So false negative, test was wrong, test said no. Test said no, but it was wrong. So what does that mean the 10 means? What does that call it? What is the 10 called? False positive. Test was wrong, it said positive. So false means the test was wrong, positive means what the test said. False positive. I don't know why I thought that would be a good. Yes?
So the areas don't correlate at all to the actual numbers.
No. They're visual representations. Oh, yes. Let's pick an arbitrary person out of the 100. If you were told, I'm telling you, I'm not telling you where this person lives, in what color, but I'm telling you that their test result was positive. The test result is positive, which means all you know is what? If I tell you the test result is positive, what does that mean? That they're either in the blue or the purple. They're in the blue circle. What's the probability that they actually have cancer? So, can you say it again? So when we have a probability, when I say that their test result was positive, a probability is you can estimate a probability by saying the number of times something happens divided by that it happened, number of times that it happened, divided by the number of total things. Crude way of putting it. I'm telling you, this person had a positive test result. How many people had a positive test result? 30. The 10 people in the blue and the 20 in the purple. All those people, the test had positive. Of those people, so that's the total number of things that could possibly happen. I'm telling you the test was positive. Out of those 30, how many of them have cancer?
20.
So if someone has a test that's positive, what's the actual chance that they're going to have cancer? 2/3, 0.66. Not great when you think about it like that, is it? Not great, 66%. This is called a conditional probability. If I tell you that a situation holds, and then I ask for the probability of something else, that's called conditional. It's conditional because the probability of the one thing depends on the other. So when I write the probability of A, and this bar means given that B is true. That's what this notation means. The probability that A, what does A mean? Having cancer. The probability of having cancer, given that their test is positive, we just deduced that it's the probability of them having cancer and the test being positive, this purple part, divided by all people for whom the test was positive. Probability of B, 20/30. So it is true that the probability of A given B is the same as the probability of A and B divided by the probability of B occurring in nature. That's an important formula that we're going to use to derive the main formula called Bayes. Are there any questions on this example? I'm sorry I'm going really slowly, but this math, I really need to make sure you get this math. Cool? Sweet.
Wait, can you go back?
Yes.
You're
Good? Okay. I just blew up the big circle, the blue circle. You can think of a conditional probability as, these were Einstein would flip his grave, changing the relative universe. If I tell you that the test was positive, we are going from this circle and zooming in to the only part that matters, this blue circle. This circle is now the only circle that matters as soon as I say the person had a positive test result. This is the only thing that matters now. The relative universe is now here. So given that our entire universe is now B, what is the probability of A? That's how we think about conditional probability. We're zooming in on a section of the universe. Also called transforming the sample space. Let's pick another arbitrary person. Now I'm telling you they have cancer. What is the probability that they had a positive test result? Don't say it out loud. Please take 3 to 5 minutes. Think. Write down an answer. Random person. I'm telling you they have cancer. What is the probability that their test result was also positive? Think about it. 3 to 5 minutes. This is like probably one of them. What? Anyone think you got an answer? No. Yes. Oh, you have an answer. Sorry. Maybe. I wasn't expecting an answer. I was just
Can we do the Seattle ring problem?
the Seattle. Oh, yeah, after the break, we'll start with that as a way to get ourselves back in it. Good. Yeah, I forgot about that. Thank you. So, who has an answer they want to share? What'd you get? What'd you get?
19 over 29.
19 over 29. Anybody have a different answer? Same answer? No answer? 5 answers? 20 over 25? 20 over 20. What did you say? Do you have one? I thought I heard you say something. Sorry. 20 over 25? 20 over 25. How does it work? If I tell you that they have cancer, B is true. I'm sorry. A, A is true. So now the question is, what is the probability that B will occur given that A has already happened? If A has already happened, that means the total amount of things that can happen is the probability of A. And then what's up here? The probability of A and B, which in this case is 20, which is the number of people who have both cancer and a positive test, divided by the number of people who have cancer, 25, which is 0.8, 80%. We now have enough information to derive Bayes' formula. We get it. Jeez. Bayes' formula, and I'm going to write it all out so it's not all in computer speak. Bayes' formula goes in the following way. It's quite simple. All we have to do is assume these two things. Well, if the probability of A given B is the same thing as the probability of A and B over the probability of B. Also, the probability of B given A is the same thing as the probability of A and B over the probability of A. I've just restated what I put down here for the purposes of erasing this. Okay. Are there any questions about these two formulations? These are the examples we just did. Two examples we just did showed these two things. Now I'm going to put them together like Bayes' theorem. The first thing I'm going to do is I'm going to multiply both sides by probability of B and probability of A. So on the left-hand side, I'll have the probability of B times the probability of A given B equals the probability of A and B. Multiply to both sides. Over here, I will have the probability of A times the probability of B given A is equal to the probability of A and B. Let's brought this over, multiplied by both sides. That's all I've done. Any questions on the arithmetic there? Guess what? Probability of A and B, probability of A and B. These two quantities are exactly the same. Fine. The probability of B times the probability of A given B now equals the probability of B given A times the probability of A. I just flip these around. Multiplication is commutative. Doesn't matter. A times B is B times A. Last step. Probability of A given B is equal to the probability of B given A times the probability of A over probability of B. And that is Bayes' formula. Simplify. Cough, cough. That is Bayes' formula. Is that we can derive one conditional probability from its converse. Whoa. Right, okay, fine. See, we're not that exciting. Until you see an actual real world example. And I'm going to walk through this example, and then it'll be break time. Yeah. Suppose you might have a rare, life-threatening disease, so you get tested. The disease test is 99% sensitive and 99% specific. Awesome. Means if you have it, the test is correct 99% of the time, and if you don't have it, it's also correct 99% of the time. Isn't that great? Sensitivity and specificity are 99%. Hell yeah. The disease occurs in 1 in every 10,000 people. Fine, whatever. Your test is positive. What is the probability that you have the disease? Because this is exactly what happens in the real world. You do not know if you have the disease. That's why you're taking the test. Sensitivity and specificity make the assumption that you have or don't have the disease. But we want the converse. This is where Bayes' theorem becomes relevant. We can use accuracy, sensitivity, and specificity to create a probability that makes more sense in the real world. This is exactly the kind of information you have. The doctor will tell you, oh, the FDA approved this test, and it's 99% accurate, 99% sensitive, and 99% specific. Awesome. That's good enough for me. The disease occurs 1 in every 10,000 people. Whatever, I have this test, which is 99% specific and sensitive. Awesome. Your test is positive. Uh-oh. Do I have the disease? You would think automatically, what? What's the probability that I have the disease? It's 99% sensitive. It's 99% sensitive. Shouldn't it be 99% chance that I have the disease? Nope. Here's why. This is why my sister went to the government and I went into math. Because she likes to exploit people, I like to show people. Nah, I'm kidding, she's great. Okay. A. Actually, I have a slide for this. The answer is 1% to kind of give you motivation to work on this problem. If you have the test is positive, you have a 1% chance of having disease. Whoa, where does that number come from? Here. Let A be the event that you have the disease. Simple enough. A, you have the disease. I have disease. Let's give it a name. The Oz syndrome. You have the Oz syndrome. It's a dance secret. It's life-threatening because you might dance to death. B is the event that you test is positive. The test was 99% sensitive. Isn't that weird? What does that mean? The probability, here's what sensitivity means, the probability speak. The probability that the model was correct given that you have the disease is 0.99. That's the catch. Sensitivity is when your result is positive, how often is the test right? Which is the same thing as saying the probability of the test being positive, B, given that you have it, is 99% chance. This is your sensitivity, folks. Make it a big deal out of this for a reason. That's sensitivity, probability. That's not what I want. That's not what I want. I want the probability of having the disease given that the test was positive. That's what I want. But using Bayes' theorem, I can find it. Because that's the point of Bayes' theorem. It's like I can find one conditional probability from its converse. This is what I want. Our formula is the probability of B given A times the probability of A over the probability of B. So far, so good, based on Bayes' theorem. Do I know any of these? Okay, here. Here's one. Equals 0.99. Do I know the probability of A? The probability that I have the disease? What's the probability of me having the disease? 1 in 10,000. 0.0001. That is the probability of me having the disease. 1 in 10,000. That's how often the disease occurs. The probability of B is a little different. The probability of B, otherwise saying, the probability of having the test be positive is not as straightforward. Because the test is probabilistic in itself. And whether or not the test is positive depends on what? Kind of. But it kind of depends on something more human. If I had it. I mean, right? Me having the disease or not affects the result of the test. That's fair to say. Whether it's a great result, I don't know, but me having the disease changes the result of the test, hopefully. How? There's only two options. I either have the disease, or I don't have the disease. The probability, and I actually might let you think about this, or I'll answer it when we get back. The probability of the test being positive. The probability of the test being positive is the following. I'll give you this answer is on the next slide. I'm aware. But if you want to work on it yourself, try to work on it during the break. The probability that the test is positive is equal to the probability that the test is positive, given that I have it, times the probability that I have it, plus the probability of the test being positive, given that I don't have it, times the probability that I don't have it. And here's what it means in words. The probability of the test being positive is the probability of the test being positive and I have it. Or the other option, the test was positive when I don't have it. Because theoretically, the test could be positive whether or not I have it or not. That's the whole point. The test could be positive regardless. So, this is why I was kind of hoping some people would read the refresher on the probability. That's fine. I'm giving you the equation. Over the break, let's take a 20-minute break. See if you can use this formula to figure out the missing probability of B completing the formula. We'll take a 20-minute break. Come back at 8:15 for the answer. We gotta get started. Next. I must ask you, Nick, I must ask you to sit down. Have you ever heard of the song Mustache by Twin Twin? Look it up. It's great. All right, so using our formula, the probability of the test being positive actually comes out to about 0.01. So whether you have it or you don't, your test will tell you that you are positive about 0.01% of the time, given a random person. And if you put all these numbers together, you actually get that if your test is positive, you actually have about a 0.0098 probability of having the disease. So that's terrifying in some sense because you're trained to believe, oh, we're 99% accurate, and that's great. But that assumes that you have the disease or you don't. If the test is positive, you can't assume whether or not you have the disease. If you could assume that, you wouldn't be in the doctor's office. So these probabilities are, and if you're an actuary, your actuary exams are literal hundreds of pages of Bayes' theorem because it's trying to find the probability that something's going to happen to you based on what we call prior probabilities. Now, there is a Facebook interview question that I would like to get through at the end of the class, but I'm going to forego it for now and for the sake of getting through what I have to get through. So, with Bayes' theorem, we can actually create a machine learning model called naive Bayes classification. Why is it called naive? We'll see. Suppose we have a data set with n features. We'll call them x1 through xn. There's n features. And a class label C. So it's classification. There's a label called C. What can we say about classification using Bayes' theorem? Well, the probability that you are in class C, given that these features exist, equals Bayes' theorem, the probability that these features exist, given that you are in class C, times the probability of class C, divided by the probability that these features exist. So we're now phrasing machine learning as a form of a complex probability equation. But notice how it's still machine learning. Because whenever we do machine learning, the question is always, given these predictors, can we predict the response? I'm just phrasing it as a probability. What is the probability that you're in class C, given that these features exist? What is the probability that you are a versicolor, given that your setosal length is this, your petal length is this, your sepal length is that, your sepal width is this? I'm just phrasing it as a probability. So Bayes' theorem can help us determine the probability of a record belonging to a class given the data we observe. That's just Bayes' theorem. This term, probability of class C, is called the prior probability. The prior probability represents the probability that any one record belongs to class C. So it's essentially the frequency at which class C exists. So if we're doing default and non-default, what's the probability that someone is going to default, period? What was the probability that someone was going to default? It was about 4%. Of all the people in the data set, about 4% of them were going to default no matter what. No matter what you predict, they're going to default. That's what probability of class C. It's a prior probability. This term is called the likelihood function. The likelihood function represents the probability of observing those features given that you're in that class. So assuming you're a Variance color, what's the probability that your sample length is this, your pale length is that, your sample length is this? Assuming that you are a Variance color. Assuming you're going to default, what's the probability that your balance is this high? It's the converse, you can think of it. It's a converse conditional probability. It's called the likelihood function. Why the square, or why the squiggly brackets? It's because there are multiple xi's. So the probability, so this one down here, the probability of squiggly bracket xi is, in words, the probability that x1 through xn occur in nature, period. So this is called the normalization constant. It's kind of like when you divide by probability of b, divide by the total number of things possible. That's called the normalization constant. It doesn't depend on c, and well, I write generally ignored. You don't ignore it from the equation, but it doesn't necessarily matter in terms of the machine learning. Because the machine learning depends on class C. So we generally focus on the likelihood function and the prior probability of a class. So we can turn machine learning into a probability question. This probability, the thing we're trying to get, is called the posterior. The posterior probability represents the probability of a data point or a record belonging to class C given that we observe this data. That's exactly machine learning in a probability question using Bayes' theorem. This idea of Bayesian inference is to then update our belief based on the distribution of C. So if one class occurs 99% of the time, like if people don't default 99% of the time and people default 1% of the time, those prior probabilities affect our posterior probability. The fact that a disease is prevalent 1 in 10,000 is super relevant to our posterior probability. The fact that 0.0001 is our probability of you having the disease, that's our prior probability, that greatly affects our posterior, which is why that number 1% was so shocking. If when I have the test was positive, what's the probability that I have the disease? It was only 1%. That number is so shocking because of the fact that the disease only occurred 1 in 10,000 people. That little statistic, which is glanced over by that 99%, that's really blown up to proportion, that 1 in 10,000 is really what drives down that number. So our prior probability greatly affects our posterior probability. Blah, blah, blah. What piece of the puzzle we've seen so far looks like it can be intractably difficult in practice? And the answer is estimating our likelihood function. Here's why. So the hard part of the problem that we just did, the hard part was what? The probability of the test being positive was the probability that the test was positive and we had it times the probability that we had it plus the probability that the test was positive given that, write the other notation, that we don't have it times the probability that we don't have it. That was long in and of itself. What if I have 20 features? What if I have 10,000 features? That equation blows the hell up. Because now it's probability that B, given that every single possible combination of A. And when I have 10,000 of these, this number becomes unimaginable to humans, but very imaginable to computers. So, how do we deal with that? Because even the computer can't handle all possible 10,000 variations very easily. It can, but not very easily. Here's where the naive part comes. The naive part says the following. Now, if you remember your probability training, Padawans, we've talked about mutually exclusive. We've talked about everything except for one type of events. What's the type of events we haven't talked about yet? Who knows? Starts with I.
Intersection.
Intersection, not quite. They're not mutually exclusive, but they're independent. What does independent mean? What does independent mean? When two events are independent, what does that mean?
You know what happened with one, it doesn't matter. It doesn't impact what might happen.
A and B do not affect each other. What is the probability that Donald Trump will be president and the probability that I'm going to go home tonight are completely irrelevant to each other. They are completely different sentences. They don't matter to each other. If we assume, naively, if we assume that every single data observation are different or independent from every other data observation, then the probability of x1, x2, x3, xn occurring becomes the following. Probability of x1 times the probability of x2, times the probability of xn. That's it. If we naively assume that every event is independent of every other event, all we have to do is multiply the probabilities together to get the probability of xi occurring. So this likelihood function, which is the hard part, here's a very simple example of when the likelihood function is very complicated. But when this is 20 or 10,000 variables, not going to work. But if we assume they're all independent, all we have to do is multiply them to each other. This naive assumption simplifies the likelihood function to make it usable, tractable. In summary, before we get to the code, the training phase involves computing the likelihood function. So when I'm about to do sklearn.fit with my naive phase, all it's going to do is pretty much this calculation. That's the hardest thing it's going to do, is do a bunch of probabilities and multiply them together. So it'll compute an estimation of the likelihood function. It'll compute the prior probabilities and the normalization constant. And then when I say predict, it's going to multiply numbers together. That's it. All it's going to do is multiply numbers together. Yep, that's it. Just multiplying probabilities to get the posterior probability, which is our answer. Let's see it. All right. Naive Bayes.py. Spam filter. Reading in our data. We have two columns. What you are looking at is a collection of spam from a couple of years ago, each with a label of ham or spam. Ham is it's good, it's fine, it was supposed to go through the filter. Spam is bad. I was not supposed to receive this. This is a spam message. You can kind of read them already. You can kind of read some of them. 6 chances to win cash from 100 to 200,000 potential. That's spam. XXX Mobile Movie Club. Use your credit card. Oh no, spam. And you remember how to spell his name? Yes, I did. Ham. So it's a bunch of messages. Some are correct. They're ham. They're fine. Some are spam messages. How many? Let's do a value count of the label. We have 4,825 ham and only 747 spam. So already we're seeing that there's much more ham than there is spam. Much more. But with naive Bayes, with our prior and posterior probabilities, that's not going to be a big problem. If we describe our message, there are 5,500 messages. Only 5,169 are unique. So some of them repeat. The most frequent message is sorry, I'll call later. Sorry, I'll call later is just a default message that some people set to when they're not available. I'll call later, which is probably why it occurs 30 times. So far, you can read the data in, you get the data. It's only 2 columns. Okay, well, you should already be asking yourself a question. Where are my predictors? The response is quite clear. Ham or spam, true or false. What are my predictors? All I have is text. Well, on Monday, we learned a way to turn text into features. You remember what that was called?
Beautiful soup.
Say it again?
Beautiful soup.
Beautiful, not quite beautiful soup. That's for going to the web and parsing HTML. It's a vectorizer. The count vectorizer, TF-IDF. Vectorizer. It's a way of turning text into numbers. We'll do an example. So before I do, I have ham and spam. I want 0 and 1. So I'm going to go ahead and map ham to 0 and spam to 1. Nothing big deal there. Now I have my label as 0 and 1. That's the big difference here. I'm going to go ahead and split these up into my training and my test set. X train, X test, Y train, Y test. Again, nothing different. 70% now exists in my training, as you can see. And I have some of them in my testing. Fine. No worries there. Count vectorizer is what I'm going to use to turn text into features. I will import my count vectorizer. I have, as a very simple example, call you tonight, call me a cab, please call me, ... please 44. Why not? I will instantiate a count vectorizer. When I fit to my train, I'm learning the vocabulary. It is actually learning the words that I'm using. And if I get feature names, here are the words I used. 44, cab, call me, please, not you. No, it did not have a ... It kept the 44. It's tokenizing my strings into words and numbers. That's what count vectorizer does. It tokenizes into words and numbers and then counts their frequency. I will take my vectorizer, which has now been fit to the vocabulary of my simple training, and I will transform it. What does transform do? It will create that matrix where each row is each sentence and each column represents a word. When I look at train simple, notice what it tells me. A 3x7 sparse matrix. What is a sparse matrix? A sparse matrix is a type of data structure. Sparse means, well, it means what it does in normal life. Sparse means that it's not very populated. It's sparsely populated. So a matrix with many, many zeros and not a lot of ones and twos and actual data points, that's called sparse. The reason it's set up like this is because soon we're about to have over 100,000 features. And for the computer to store 100,000 by 5,000 sentences, that's a lot of memory. So in order to save on that memory, it's going to convert it to a sparse matrix object to cut down on your computer's RAM so you can have 1 million. I mean, I've had this up to 2 million features. But because I'm only looking at 3 sentences with 7 words, let's actually look at it. In fact, here it is as a data frame. Each row is a sentence. Each column is a word. So that first sentence, call you tonight, is represented here. Call you tonight, first row. Second sentence, call me cab. It took out the stop words. Second one, please call me please 44. So it's just counting the tokens. Notice it takes care of lowercase, uppercase, takes out stop words, takes out all this stuff. Cool. Awesome. Fantastic. Shazam. Great movie. Shaquille O'Neal. Now, here's the interesting part. That was our training set. Here's our simple test set. Please don't call me. Please don't call me. One testing. Vect has learned my training set. Vect has learned my training set. What are the words that Vect knows? Please call me. What else? You cab 44. Those are the only words it knows, because that's what I gave it as a training. This testing set has new words. What new word does this training set have? Don't. Don't is a word that did not exist in the training set. So what's going to happen? I'm going to tell my Vect, which only knows 7 words, to transform itself to my testing data. If we look at it, this is what the vectorizer spits out. Your new sentence is me, please, call me, please. It doesn't know the word don't. It's never seen it before. So when it saw it in a test, it disregarded it. So your vectorizer will only learn the words given to it in a training set. Now, what do humans like to do again? Acronyms, make up words. We misspell everything. We don't care. We love to misspell things. If we use a word that was not used yesterday, our vectorizer will not pick it up. So these types of training methods will have to reteach themselves every couple of days to understand the new lingo that the cool kids are using. Okay. Does that paradigm make sense? The count vectorizer was given 3 sentences. 3 sentences. It had 7 tokens in it. So the vectorizer learned 7 tokens. When it was asked to transform to a new sentence with the word don't in it, it had never seen the word don't. So it completely disregarded it and only looked at the 7 words it knew. Well, that's boring, only 7 words. Let's do it with our SMS data. So this data is actually their text messages, their text spam. I will make a count vectorizer, vect. In one line, I'm going to fit and transform my training data. So this count vectorizer is not machine learning yet, per se. Count vectorizer is turning text into features. It's turning text into features. That's what I'm writing down. Count vectorizer is taking in text and spitting out a matrix. The matrix is about to be thrown into a naive Bayes, out of which will pop probabilities. The count vectorizer part is not the machine learning yet. It's turning text into a matrix. Why a matrix? Well, that's what data frames are. That's our predictors. It's about to be our predictors. If we look at it, how many things were in our training set? 4,179. So now we have a 4,179 rows. That's how many rows were in, how many sentences were in our training set. How many tokens did it find? 86,489. So in those 4,179 sentences, it found over 86,000 different tokens. And I'm not going to turn this into an array because it won't mean anything. All right, I will. Just a bunch of zeros. That's how sparse it is. Because in 86,000 tokens, every text, every message probably has like 10 or 15 words in it. So each text has 86,000 numbers attached to it. If that word did not exist in that text, it's just a 0. If it occurred once, it's a 1. If it occurred twice, it's a 2. If it occurs 0 times, it's a 0. So each text has 86,000 numbers attached to it. So we're looking at a 4,179 by 86,489 matrix. I'll take my same vectorizer, which has now learned. How many words has my vectorizer learned? 86,489. That's how many words it knows. That's how many words it knows. I'm going to transform it to my testing set. Yes, it was. I'm going to transform it to my testing set. Before I look at it, you can tell me with 100% accuracy, test DTM, which is our vectorizer fit to the testing data. How many rows will it have? How many columns will it have? Well, if the training had 4,179, where did that number come from? Training. That's how many training sets there were. So how many rows do you think are in the test one? I'll give you a hint. We'll look at it before. You scroll up, it'll tell you. How many data points were in the testing set? Say it again? 1393. How many words does it know, the vectorizer?
7,456.
It knows. Yes. Thank you. 74. 56 words. Perfect. There were 1,393 sentences in the testing set. And it only fit to the words it knew. It only fit to the words it knew. Does that mean there are 7,456 words in the testing set? No. There could be more, there could be less. But it's fitting it to the words that it knows. So if there was a new word in test that had never been seen before in training, it got dropped. It can't use it because it has never seen that word before. To kind of look at it, there are, again, 7,456 words that it knows. Here are the first 50. These are words as defined by the actual messages. These actually existed in the messages, so it's thinking these are words. Why not? They're words. It doesn't know any better. We could tell it. So part of the advanced features of count vectorizers is we can tell it how to tokenize. And we can say, don't keep numbers. We could say only use words. But the base count vectorizer will count numbers as words. Here are the last 50. yourself, you wanna, your wife's, yo, you, your, yours, you, I thing, yum. I don't wanna. Who knows? We can look. So here I'm turning our training into an array, a physical large NumPy array. It's not crashing my computer, but it's still, it can't even show me all the numbers because there's so many. Here's some simple summaries of the training data. A little refresher on NumPy first. So here is a NumPy array, a two-dimensional array with 2 rows and 4 columns. Remember this notation? Uh-oh. Array 0, 0. What number will that give me? 1. What will array 1, 3 give me? 8. Remember this notation? 0, colon. Which means the 0. So anything before the comma is the rows. Anything after the comma is the columns. So before the comma is a 0. So what row are we on? 0, first row. And then it says what columns? Colon, which means all of them. So what is this going to give me? The entire first row. 1, 2, 3, 4. Before the comma, we have rows. Which rows do I want? All of them. After the comma is a 0. Which column do I want? So what is this going to give me? 1, 5. First column. What is the sum of my two-dimensional array? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, which is 36. If I sum it across axis 0, 0 means column, so I'm summing for each column, so it's going to go 6, 8, 10, 12. If I sum my array based on axis 1, which is rows, I'll get the sum of the first row, which is 10, and the sum of the second row, which is 26. Why does that matter? Well, xtrain, the first element of xtrain is this. Go until during point, crazy rubble, only boogies in the gray world, lava phase, whatever. That's a text message that someone once received. In the training array, we can calculate the number of tokens that was in this message, and there are 24 tokens. According to our tokenizer, there are 24 tokens in this array. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You get rid of the dots. 20 tokens. Where are the 24 coming from? Say that again? Well, this is the 4 words that I want, I'm sorry. Well, this is the training data. So this is where it's learning from. It's learning from the training set. This is the first message in xtrain. This is xtrain 0. This is the first message in our data frame. This sum, train array 0, comma, so first row, all the columns, all 7,400 of them. If you add them all up, you get 24. So it thinks there's 24 tokens in this thing. Why? It has its own built-in tokenization function that we don't control. We can give it our own, but if we don't give it one, it has its own default. By default, for example, so we have 1, 2, 3, 4, it actually will count dots versus dots. And if there's a dot after a buffet with no space, it will split those up into 2 different tokens. So it has its own tokenization. Question?
Was I supposed to get that same message?
Yes.
We're not
Oh,
getting it. I got four.
is it because it's
half
sweet?
price.
The what?
Orange line rental.
You all have the orange lime rental?
Yes.
No? You do have? Does anyone have what I have? Guys, what are you doing? Code. That is interesting. Why am I the only person? This is what I got this morning too. It's the same sentence.
Yeah, like our output is still 24.
You got which one?
Our output is still 24. Yeah.
Yeah.
Yes.
But your X train 0 is different?
Yeah.
Interesting. See, this is why I should theoretically go over this with other people before going over with you, but I'm the only person I know.
Do what?
4 months, half
No,
price.
it's not.
That's interesting. Okay, that's fine. That's what you see, right? 4 months, half price, orange line rental.
Yeah.
Okay. That's very interesting. All right, I don't know. That's what's going on. Oh, yeah, apparently. Well, that one must have 24 tokens. Because earlier today, I was like saying, there's not 24 tokens. That's weird. It must be counting the ... dots. But now I know, nope, it's just giving me the wrong sentence because that sentence only has 20 tokens in it. That's fine. Okay, well, yours is correct then. That's fine. Your sentence is correct. It has 24 tokens in it.
Yeah.
What is your train features? 0.
Is there a chance you have as a data frame that's getting the index 0 instead of the array location 0?
But why would theirs be different than mine? Same exact code.
Because when you print X train, I show an umpire and you show a data frame.
I don't know. We'll think of it later. I'm sorry. I want to get through everything. Sorry. What is your train feature 0?
That.
This?
Yes.
0, 0?
Yeah.
Okay. Well, whatever. Okay. Well, each row is a sentence or a message. Each column is a token. So when I sum the first row, I'm getting how many tokens are in the first message. If I sum the first column, what am I getting? If I sum the first column, what am I getting? Bless you. If I sum the first row, that's how many tokens there are in the first sentence. If I sum the first column represents the first token. The first token is 0, 0. What does that tell me?
The amount that token is occurring within all the messages.
5 times. 0, 0 as a token occurs 5 times in my 4100 training sets. That number's right. This is how many times each token appears across all messages. So the first token appears 5 times, the second token appears 23 times. Let's actually put it in a data frame. Train token counts. So now we can see the tokens and their actual prevalence. I'm going to sort it. So the word to appears the most often. You, the, and, in is the, me, it, my, for, you, of, that, call, blah, blah, blah. Again, if we filter it based on when the token is 0, 0, thank God we have the same 0, 0, that will also give us 5 times that this actually occurs in our data set. So we just turned text using a count vectorizer into a matrix. A matrix with 7,400 columns. Now we can use machine learning by taking that matrix and turning it into predictions. So from scikit-learn, we have our naive Bayes. It's called multinomial NB. Why? Because the naive Bayes can handle more than one classification, whereas it's generally meant to only handle 2. So scikit-learn just called it multinomial NB. But multinomial NB is their naive Bayes. At this point, it's no different than anything else we've done. instantiate, fit to our training, predict our test, and here's our answers. There's a bunch of zeros and ones. 0 being not spam, 1 being spam. Well, it's classification, right? What's our accuracy? 98.8%. Okay. So far, we're taking that with a grain of salt. Here's our confusion matrix. Can someone tell me my true positives?
174.
174. Where are my true negatives? 1203. What is 11?
False.
I hear false positive. Does anybody agree or disagree?
No.
What is the first
False negative.
false negative? What is 5?
False
False
positive.
positive.
False positive. I will predict proba. These are my predictions, probabilities for each one based on my naive base. This is my probability that each message is a spam. I can use it to make an ROC score, 0.986. That's very good. That's my AUC, area under the curve. The closer to 1, the better. Note, I didn't give it my predictions, I gave it my probabilities. Because it's trying all possible thresholds, computing the ROC curve, and then calculating the AUC, the area under that curve. Here are all the false positives. Wait. Oop. Stop. Here are all the false positives, all 5 of them. Remember, on the top right, here are all 5. So here are the, so if it's a false positive, what does that mean?
I just thought it was spam.
It thought it was spam, but it was false. It was wrong. Waiting for your call, also Andros, ICE, etc., no calls, message, missed calls, no pick, please resend, no calls, message, missed calls. It thought those were spam, but they were not. Here, and the way I got it was the following. X test, when Y test was less than predictions. Prediction is 0 or 1. Y test is 0 or 1. A false positive is when the test, a false positive is when the model said yes, so our prediction was 1, and our test was 0, it wasn't spam. So anywhere where the prediction is 1 and the Y test is 0, these are my false positives. This is a little trick for binary classifiers. There's only 2 responses. Likewise, if it was a false negative means the model said, no, this is not spam, but the model was false. It was wrong. The model, it was actually spam. So if it was a false negative, that means our prediction was 0, ham, but our Y test is 1. It was spam. So anywhere where the Y test was 1 and the prediction was 0 are my 11 false negatives. And you can see, to us maybe they're slightly obvious. Hi, I'm Sue, I'm 20 years old and I work as a, oh God. Hey babe, next you forgot me, about me, scammers getting, so I mean maybe to us they're a little bit obvious, but machines aren't that smart. Come on, give it a break. Listen to extreme dirty I don't want to keep going.
You not prep for these.
What?
You not prep for these.
Oh, of course I did. Of course. All right. So far, The only quote-unquote novel thing I've done is use the count vectorizer to turn text into matrix. Because we have to remember what we started with. We started with a data frame with 2 columns. Ham and spam was one column, and the other column was just text, was messages, words. The cool novel thing we did was turn all of that text, which was one column, into a matrix with 7,456 columns. We used 7,456 predictors to predict our response, which was only 0 or 1. Naive Bayes has a lot of pros. Number 1, it's really fast when you have a lot of predictors. We're going to do a speed comparison in a second. It's really fast at doing 1,000,000 predictors or more. Why? Because all it's doing is multiplying probabilities together. All it's doing is multiplying 1,000,000 numbers together, which to us, obviously that's hard, but to the computer, that's nothing. It's really fast and you have a lot of predictors. Naive Bayes is also very useful when your distribution of your classes is uneven. So right here, for example, of all of my messages, about 90% of them were ham, only 10% was spam. That's very uneven. And the defaulting, as part of what I'm going to give you as like an optional, if you want to do more exercises with this, for your defaulting is a very uneven class structure. So the naive Bayes will likely handle that much better because the whole idea of the prior and the posterior probability. The whole idea of the disease being prevalent only 1 in 10,000 people actually affecting our posterior probability, that's what makes Bayes and naive Bayes very, very popular. So, let's compare naive Bayes to logistic regression, because why not? We're now at a point where we can start comparing models to each other. We're going to compare logistic regression to naive Bayes. I'm going to take my vectorizer and I'm going to fit it to everything, to all of my messages. I'm going to take my vectorizer, which has learned how many words? 7,456. That's how many words it learned. Can someone tell me how many columns I'm going to have when I look at this variable? How many columns am I going to have? How many words is it now? Oh, I'm sorry, you're right, 8,713. I'm sorry, that's my fault. And how many rows? 5,572. What this is telling me, there are 8,713 tokens in all of the messages. In all the messages, there are 8,713 tokens. 5,572 rows, messages. I'm going to import my logistic regression. Now I have logistic and naive Bayes. I will instantiate a logistic regression. I'm going to use AUC to compare. Because what could happen is that logistic regression might work better for a different threshold than naive Bayes would for a separate threshold. So I'm going to use my ROC, AUC, my ROC, to compare across classifications. The biggest advantage of ROC is comparison across classification models. It is a much better metric for comparing across classification models than accuracy or sensitivity or specificity. Cross-val score of the naive Bayes. Could you? So selfish.
Trying to save people.
Just trying to teach. Cross-val score of the naive Bayes, given all of my data recall all DTM is actually a matrix with 5,572 rows and 8,713 columns. It's just like any other matrix you would put into Crossfile Score, just with a lot more columns. K is 10, 10 folds, and scoring ROC, AUC, mean. Here's the NB, 0.9832, and here's the logistic regression, 0.988. Notice two things. Which one ended up being better? Logistic regression. Never said naive Bayes was better than logistic regression. Did anyone else notice anything else? All right, I'm going to do a countdown. Ready? 3, 2, 1. Okay. It's faster on my computer because of the lag, but it'll still make a point. What? I guess. How do I use it? So like this. So one loop, so 796 milliseconds. Fair enough. Thank you. Now I'm going to time it for my logistic regression. Take your time. 2.67 seconds for 8,700 words. Naive Bayes, thank you so much. That's awesome. Did it in 796 milliseconds, less than a second, whereas the logistic regression took 2.5 seconds to do it. Sure, fine, I can wait the 2 seconds, by all means. But what we're about to do is we're going to get a lot more features by adding in a new parameter called n-grams. So far, all I've done was look at each word. Now, you might have been asking yourself, well, Sanon, words can indicate spamminess, like winner, or scammers, or XXX. So, these things generally tend to predict spam or ham. But what about 2-word phrases, or 3-word phrases, 4-word phrases, 5-word phrases? You're a winner. You're a winner is a phrase of 3 words, but our count vectorizer doesn't know that phrase. It knows your, it knows a, and it knows winner, but it doesn't know you're a winner. Count vectorizer can also take in n-grams. N-grams, well, it stands for n-grams. An n-gram is an n-word phrase. So a 1 gram is a word. A 2 gram is a 2-word phrase. A 3 gram is a 3-word phrase, like are a winner, I have a. Those are 3-word phrases. So I'm going to give it an n-gram range, of 1 to 5. So I want single words, 2-word phrases, 3-word phrases, 4-word phrases, 5-word phrases. And I'm also going to tell it to take out any English stop words, like of, and, the, and. 2 new features. Well, we saw the stop words last time on Monday. But the n-grams is new. So I'm going to tell it to remove stop words and also look at up to 5-word phrases. So I make my vectorizer. I'll transform it to my X-train. So now it's learning the vocabulary. It's learning all the words, all the 2-word, 3-word, 4-word, 5-word phrases. Still 4,179 rows, now 86,000 columns. So we went from 8,700 to 86,000 columns. Because now it's looking at up to 5-word phrases at a time. Like, you are a winner, bro. I will transform it to my X test So now my X test is also, again, taken under the respect of those 86,489 tokens that it knows. There might be a 5-word phrase that exists here but not in train, but it doesn't matter because that 5-word phrase gets taken out. I will instantiate my multinomial NB, my naive Bayes. I will fit to my training set, predict my test set. Look at my accuracy, 0.99, which is a lot better. And now my confusion matrix, look at that. My ROC, I'm going to compare it to logistic regression. Here are my false positives. So here's where the spam detector said, yes, it was spam, but it wasn't. We'll purchase the stuff today and mail to you. Here are the false negatives. Can someone explain what false negative means again? The system said what? The system said negative, so not spam, but it was actually. So here's that same message. Hi, I'm Sue. Sue's good. Sue's very good at what she does. I convince you that she's a 20-year-old girl working as a law. She's very good at that. Let's compare logistic to naive Bayes now with 86,000 columns. So I will train it against all of my messages up to 5 grams. And this even takes a second to learn all of the 5 up to 5 grams. Now there's 110,000 columns. We run the test naive Bayes versus logistic regression for 110. And this is only for 5,000 messages. If you're looking at the last million tweets, forget about it. This is going to be 2 million easy. 2 million easy 5 grams. Easy. Fine. Logistic regression. Let's do a time it. This new feature we've just learned. Let's time the naive Bayes under 110,000 columns. It's still thinking, it's doing several loops. 1.73 seconds. Still beats the 8,000 from logistic regression. I'm almost terrified. Not that terrified. Let's take a 20-minute break and come back. But actually, we might be here for a little bit. So let's have a chat. How old do you think I am? No. So what it's doing, from what I can gather, it's doing it 3 times, and it's taking the best trial. So this might actually take about a minute, but we're about to see how much faster naive Bayes is at performing under 110,000 columns. Why is logistic regression taking so long? What is it doing in the back end that took 10 seconds to do? 10 seconds was the best time it could do for 110,000. What is it doing in the back end? Do you remember? What does logistic regression do? I'll give you a hint. It's why it's a misnomer. It's why it's called regression, but it's not actually regression. What is logistic regression doing in the back end?
Log odds.
It is doing log odds. To what? Well, what is it doing with log odds?
So, building
Close. Put those two together.
assigning a score of class, the probability of class using log odds.
It's doing a linear regression between your columns and the log odds of your response. So it's still performing the same mathematical computation of a linear regression. What is the mathematical computation of a linear regression? Matrix operations. When you have a matrix of 110,000 by 110,000, that takes a while to compute. But with naive Bayes, what does it have to do with 110 numbers? Just multiply. When it fit and transformed, it calculated all the probabilities. So now when it comes down time to test, or rather predict, All it's now doing is just multiplying those numbers together in different orders to give you these numbers. It's using Bayes' theorem to calculate all these numbers. And what's more, oh, it doesn't actually tell me the answer? I'll have to do it again to get the actual answer. That one didn't take a while. All right, well, this might take 10 seconds, apparently. So our cross-val score is now 0.9944 for our naive Bayes. It was really good. Our logistic regression is 0.989. Sure, it's also really good. But not only is naive Bayes generally faster for more predictors, it's generally more accurate. It's generally more accurate when you have a lot more features, and also when your class distributions are very uneven. When you have uneven class distributions, naive Bayes is generally a better fit. Doesn't mean you should stick to it and only do that. You should test it against other models like I just did. So, we've just done a text spam classification with logistic regression and naive Bayes. Which would you choose? Why naive Bayes? Not only is it more accurate, it's way faster. When Google has to look at, God knows how many billions of Gmails a day, billions of emails a day, it's going to choose the thing that takes 10 times, that is 10 times faster. Naive Bayes was 10 times faster on average than your logistic regression. So in scale, in production, a naive Bayes classifier is going to be way better. We have some. Now I'll ask you a question. Yes?
I have more just a question.
Okay.
For the cross-val, what I'm trying to wrap my head around is, I know you just ran naive Bayes, but you only instantiated the logistic regression just one line above. So just by using cross-val score and having logistic regression there, and then your data set is just specified as all BTM. Is that all you can do? You don't need to do the same set of steps that we've done previously where we do the fit and predict. You see what I'm saying?
Cross-val score, well, you've done this before too. Cross-val score always only takes in a blank model, all of your data, all of your responses, and a K, a cross-validation number. Because what is this doing in the back end? 10 times it's training, it's fitting and predicting. 10 times it's fitting, predict, fit, predict, fit, predict, fit, predict, 10 times. So you don't give it an already split up data set. You always give cross-val score all of your data because it's going to split it up into 10 different sectors for you. So whenever you use cross-val score, so you've used train test split, right? Train test split, you do it manually once. Cross-val score does train test split 10 times for you in a row, and then averages the results. Does that make sense? Cross-val score will always take in all of your data and then split it up for you automatically 10 times. Cool. For the remainder, so the next 10 minutes, try to do a naive Bayes classification on your own using this data. But try to do it from n-grams with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and print out your ROC AUC results for each one. So try an account vectorizer with 1 grams, try account vectorizer with 2 grams, 3 grams, 4 grams, 5 grams, up to 10, and then for each one, do a naive Bayes and print out your ROC AUC. You can either use a grid search or your own for loop to do something like this. So go ahead and try that. We'll do that until the end of class. There's extra stuff at the bottom, but I'm not going to do that today.
So what happens if you now? Because it's going to just do it over again. Okay. Without your. Oh, so this is the right. Yes. So it's going to do it
It's infinite predicted these times. Doesn't matter what I said before. It's a good video. Oh, we can do it at the end. Oh, sure. Another one. So the first thing I always do is get stats. It's really weird. Okay, so it's kind of weird. Yeah, it says so if it was it had to.
So it's
Star all-star, yeah.
centering. But it's also that so make you that automatically. Yes, let's do this.
There's a limit.
I know, it's like new computer, so it just like does everything right now without anything, but
Seeds get up. Every file has to be one. This is file size.
Standardizing things.
So even if you ignore it, it's still gonna how I estimate it a bit longer to get up so that when we look at it, we can see. I mean, it is a cattle, so like we can always tell it it's not. Yeah, like it's more work than necessary. Or Dropbox, even at this point, if you want to get Dropbox.
Can you do like maybe already says you
No, I don't do this, right? You leave the link in Dropbox and the link to CSV. So you want to open your Dropbox and you want to just go to the Dropbox and link. That will go to your type of Dropbox and the CSV.
I'm actually sorry, I'll show them.
So why don't you do that at home?
They use some different computers, right?
Do that at home. How's it going? Figure out Java, CSV stuff? So what did
You know what I'm saying?
Yeah,
So you see the
Yeah.
results and results.
I saw that they chose 3 segments.
Right, but I was saying,
All up and then not. No, it's 2 is what it is.
I mean, okay, I'm not even and so before that, I was saying, there's cross results and word results. So those are like results for races.
In the
that
cross-stream or
No. That's based on races. So not Strava, not related to Strava.
just races? Okay.
So yeah, so like word results. So when you do your race,
Then you get the data for the first
so the race organizers have to submit
Fair enough.
the final, right? The final results, and then what they do is will take all, so they will, so you put this in the thing, let's say this person did these races, and then you put in like an upcoming race. Well, you actually don't put in like, they said if you put in an upcoming race, it says, these are all the races, right, should be this race.
Fair enough.
This person should say, says first one, second